Singularity. At the center of every black hole lies a singularity, a point where all the black hole's mass is concentrated into an infinitely small space. The density here becomes infinite, and gravity becomes so strong that it warps space and time infinitely. Physics as we know it can't describe this place. Our equations simply stop working. It's like dividing by zero. Everything breaks down, and no meaningful answer exists. Current theories suggest that inside a singularity, matter is crushed to a state beyond subatomic particles. It's a region where both quantum mechanics and general relativity fail, making it one of the greatest challenges in modern science to understand. Spaghettification. Near a black hole, gravity pulls on you with incredible strength. The part of you closer to the black hole feels a stronger pull than the part farther away. This difference stretches you into a long, thin shape. Scientists call this spaghettification. First, your molecules are torn apart, then atoms, and finally atomic nuclei. Some sources claim spaghettification only happens near small black holes, but this isn't true. It happens in all black holes, though smaller ones cause it earlier. For supermassive black holes, the stretching begins much deeper inside, where gravity becomes strongest. Regardless of size, nothing escapes becoming cosmic spaghetti. Event horizon. The event horizon is the invisible edge of a black hole, often called the point of no return. Anything that crosses it, light, matter, or even entire stars, loses all connection to the rest of the universe. It's as if it vanishes forever. The black hole's gravity is so strong that it pulls everything inward, even light, which is why black holes appear completely black. To an outside observer, the event horizon looks like a boundary hiding everything inside. Beyond this point, space and time stretch so much that nothing, not even the fastest thing in the universe, can escape. It's the ultimate cosmic trap. Frozen time. Close to a black hole, time behaves in extreme ways. To someone watching from far away, an object falling toward the black hole seems to slow down endlessly as it approaches the edge. The object appears frozen in time, stuck just above the black hole's boundary. Its light becomes dimmer and redder until it fades away completely. This happens because the black hole's gravity stretches time so much that, from the outside, it almost stops near the edge. But for the object itself, time feels normal as it falls. This shows how black holes bend not just space, but time itself. Only 2% of viewers can like this video and subscribe to the channel before the timer gets pulled into a black hole. Drop a comment saying "done" if you escape the pull in time. Hawking radiation. Black holes don't just trap everything, they also slowly lose energy. This effect, called Hawking radiation, was discovered by physicist Stephen Hawking. Here's how it works. Near the event horizon, quantum particles pop in and out of existence in pairs. Normally, they cancel each other out, but sometimes one particle escapes while the other falls into the black hole. To create the escaping particle, energy is taken from the black hole itself. Over time, this loss of energy makes the black hole shrink. If this process continues, the black hole will eventually evaporate completely, fading away one particle at a time. No hair. Black holes might seem mysterious, but they're surprisingly simple. The no-hair theorem says they can only have three properties: mass, rotation, and electric charge. Mass tells how much stuff is inside, rotation shows how fast the black hole spins, and charge explains its electric properties. Everything else, like what the black hole swallowed, gets erased. It doesn't matter if it formed from a star, gas, or planets. Black holes end up smooth and featureless, like identical spheres. This simplicity is what makes them so unique. While stars and planets have distinct features, black holes hide every detail except these three basic traits. Information paradox. Black holes create one of the biggest mysteries in physics, the information paradox. In physics, information means the unique details about matter, like what it's made of and how it behaves. According to the laws of physics, information can't be destroyed. But when something falls into a black hole, all that information seems to vanish forever. This breaks the rules of quantum mechanics. Stephen Hawking suggested two possible solutions. The first is that information might escape as radiation over time. The second is that it could be stored on the surface of the black hole, the event horizon. Solving this paradox could help bridge quantum mechanics and Einstein's theory of relativity, two pillars of modern physics. Jets. Some black holes unleash colossal beams of energy called jets. These jets, moving at nearly the speed of light, are powered by the material swirling around the black hole in the accretion disk. As this material heats up and spins, magnetic fields channel some of it away, forming jets that blast outward. They can stretch for thousands of light years, long enough to cross entire galaxies, and shine brighter than the combined light of billions of stars. Jets don't just look spectacular, they shape their surroundings, affecting star formation and even the growth of galaxies. Mini black holes. Mini black holes are unlike the giant ones formed from collapsing stars. Scientists think they might have formed right after the Big Bang, when the universe was extremely hot and dense. These black holes would be tiny, smaller than an atom, but with incredible mass packed inside. Some theories suggest mini black holes could still exist today, moving through space unseen. If one passed through Earth, it wouldn't cause destruction but might leave detectable signs like tiny shifts in gravity. Nothing falls. When something enters a black hole, its motion changes in surprising ways. Beyond the event horizon, space and time are so warped that every possible path leads straight to the singularity. This is like how an apple falls to Earth. It follows the curve of space-time. But inside a black hole, the curve is so extreme that there's no stopping or turning back. Everything moves inward, not because it's being pulled, but because space itself flows toward the center. Even at subluminal speeds, the singularity becomes the unavoidable end. Stardust. Black holes and supernovae work together to shape the galaxy. When a massive star explodes as a supernova, it ejects heavy elements like carbon, oxygen, and iron at incredible speeds, close to the speed of light. These explosions spread essential elements into space, laying the groundwork for new stars and planets. Black holes amplify this process. Through their powerful jets and intense gravitational pull, they scatter these materials even farther across the galaxy. Together, supernovae and black holes ensure the galaxy is enriched with the elements needed to form everything, from planets to life itself. Share this video with someone who loves learning and click on the next one to keep exploring.